In this video, we'll be looking at the remainder of the problems in the 7.6 Achieve assignment. That'll be problems 7 through 17. For number 7, it's a bit of a tricky one. We have the integral of x to the 1/2 divided by x to the 1/3 plus 1. We're trying to integrate that with respect to x. So what I did in this problem when I was thinking about how I was going to approach it is I just looked at the degree difference in the numerator and denominator, and I said, well, if I took x to the 1/2 and I divided it by x to the 1/3, that's x to the 3/6 minus 2/6 gives me x to the 1/6. And then I was thinking, if I allow u to equal x to the 1/6, then x to the 1/3 would be u squared, and x to the 1/2 would be u cubed. So I'm thinking, hey, that'll get rid of the fractional exponents in this problem. It should allow me to work it much more easily. Let me go ahead and make this a large screen. So I went in and tried the u substitution. Let's let u equal x to the 1/6 power. Well, of course, the derivative of that is going to be 1/6 x to the -5/6 power with respect to x. Now I have a dx in there, so I went ahead and I solved this equation for dx. I said, well, if du is equal to this in terms of dx, if I try to get dx on a side by itself, I would have to multiply by 6 and by x to the positive 5/6 powers on both sides, and I would get dx is equal to 6x to the 5/6 du. Now I know if u is equal to x to the 1/6, then u to the 5th is going to equal x to the 5/6. So that allows me to see that dx is nothing more than 6u to the 5th du. I go back into my problem. Like I said earlier, if x to the 1/6 is u, I know this is the same thing as x to the 3/6, so that means it's the same thing as u cubed. So I can say, all right, x to the 1/2 is u to the 3rd. My dx is my 6u to the 5th du. Now my denominator, the first term is u squared plus 1. So I can say, all right, now I can factor that 6 out of the numerator, and that's going to leave me a u to the 8th over that denominator. I'm still trying to integrate it with respect to u. As soon as I see that the numerator is way greater degree than the denominator, I know I need to use long division. So I divide u squared plus 1 into u to the 8th. U squared goes into u to the 8th, u to the 6th times. When I multiply out, I get u to the 8th plus u to the 6th. I have to remember to subtract that. The u to the 8ths cancel, but I'll have minus u to the 6th. I keep on going. U goes into negative u to the 6th minus u to the 4th times. Negative u to the 4th times u squared is a negative u to the 6th. Negative u to the 4th times 1, I get my minus u to the 4th. We subtract that out, and when I do, I get a positive u to the 4th left over, and I know that u squared times u squared will give me u to the 4th. That will cancel out, but I'll also have plus u squared that I have to subtract out. So when I subtract that out, I get a negative u squared left. Well, u squared will divide into negative u squared -1 time. -1 times u squared will give me my negative u squared. -1 times 1 minus 1. Again, and I didn't show it here, and I should have, we remember to subtract out that last group there, and when you do, you'll get a positive 1 left over. Okay, so now I can say this is all what's inside of that integral. It's going to integrate to this with this as a remainder still divided by that denominator. That's what I tried to show here in my next step. My integral is going to equal 6 times the group, and the group is going to be the integral, the part that divided evenly, this part right here, integrated with respect to u, plus, this is still all multiplied by 6, the part of this integral that did not integrate, or that did not divide evenly, the 1 over that initial denominator of u squared plus 1. Well, now it's easy to integrate because I can say these are all just power rule, and this is by definition an inverse tangent function. So I just get u to the 7th over 7 minus u to the 5th over 5 plus u cubed over 3 minus u plus the inverse tangent of u plus c. And then when I tried to evaluate that, we distribute through the 6 everywhere. You'll get 6/7, and we know u is x to the 1/6. So u to the 7th is going to be x to the 7 over 6. Power to a power, you'd multiply 7 times 1 over 6 is 7/6. And then you're going to have minus 6/5 x to the 5/6 for u to the 5th. And then you're going to have plus 6 over 3, that's going to be plus 2. And then you're going to have x to the 3/6, which is just x to the 1/2. And then minus u becomes minus 6 times x to the 1/6 there. Then I didn't want to run into my long division problem, so I went down here and I said plus, I don't know why that 6 is so ugly there, plus 6, and we'll have inverse tangent of x to the 1/6 plus your constant of integration. Gorgeous problem there. And now just to double check with Achieve, notice that that's precisely the way I entered it into Achieve with the fractional exponents. And of course, since the original problem was in terms of fractional exponents, your answer should be as well. For the next one here, number 8, as soon as you see the natural log in there, you should be thinking, John, we're going to do integration by parts on this one. Absolutely. So when you're looking at this one, you have the integral of x to the 4th natural log of x dx. Let u equal the natural log of x. We know the derivative of that is going to be 1 over x dx. Well, dv has to be everything else in there. So it's the x to the 4th dx. When you integrate that, you're going to get x to the 5th over 5, or just 1/5 x to the 5th. So now, in my solution, I can say, well, then the integral of this should be u times v. Well, u times v, I went ahead and put the algebraic function first. 1/5 x to the 5th, natural log of x is my u times v. And then minus the integral of v du. Well, that's going to be minus 1/5. The integral of x to the 5th times 1 over x just gives me x to the 4th on the inside, integrated with respect to x. And then that's easy because you can just say, well, that's power rule. That's going to be x to the 5th over 5. That over 5 multiplies the 1/5 in front of it, and I get minus 1/25 x to the 5th for the second term. Add in your constant of integration, and you're done with that problem. 8 was kind of anticlimactic compared with a lot of other questions on here. For number 9, the problem that you're given, and you might just immediately recognize that the problem that you're given has an irreducible quadratic in the denominator. The x squared plus 10x plus 89, it's always positive. It has no x-intercepts. So I can say, well, if I have an irreducible quadratic factor in that denominator, I need to go ahead and work with that. Now, there is no need trying to do any method of partial fractions on it, because you can say, well, you don't need to worry about an ax plus b. We already know the numerator is simply just a 1. So you say, well, all right, what do I do with this fraction then? I need to complete the square in the denominator. So you say, you need a perfect square trinomial down there. In order to obtain that, the constant that you need is always half of b squared. Well, half of 10 is 5. 5 squared is 25. I want to see a 25 on the inside of that trinomial. So on the outside, that 89, I have to subtract a 25 since I'm adding 25 on the inside. Now, this trinomial can better be written as x plus 5 quantity squared. That's equivalent to this. And then on the outside, 89 minus 25, it's going to give me a 64. So then I can say, well, then my original problem is equal to the integral of dx over x plus 5 quantity squared plus 64 squared. And I can say, this is in the format of 1 over u squared plus a squared, where I can say my answer is just 1 over a inverse tangent of u over a plus c. You'll see I said formula number 16. It is formula number 16 from your table of integrals, where u is just the group x plus 5. So you say, well, 1 over a, that's the square root of this number, 1 over 8, inverse tangent u, which is x plus 5, over the square root of this number, 8, plus your constant of integration. If you do that, you'd be doing great. You can see it's a pretty simple, quick answer there. The next one, not too bad either. We have the square root of 12x squared plus x to the 4th integrated with respect to x. I did that on another sheet here. So now, in order to look at my work in this problem, the first thing I did here is recognize that, well, I have a common factor of x squared inside that square root. So that x squared, the square root of x squared can come out as an x. And so then I can say, well, then this original problem is equal to the integral of x times, now when you factor out the square root of x squared, you're going to have left 12 plus x to the 2nd. Now we're integrating that with respect to x. I recognize that, hey, the derivative of what's inside is already almost on the outside. So I'm going to do a u substitution. Let's let u equal the part on the inside. And then du would be 2x dx. I don't have a 2x dx, and I didn't have room to go ahead and force it here, so I did it in another step. I need to multiply the inside by 2 and divide by 2 on the outside. Now I know that this 2x and this dx are going to become du in the next step. My square root's just going to become the square root of u, which I can more easily call u to the 1/2 power, since I'm going to have to use the power rule on it. Now, in using that power rule, we'll have 1/2, and then this is going to become u to the 3/2 divided by 3/2 means times 2/3. So I get 2/3 u to the 3/2 power there. And then I can say, well, all right, plus my constant of integration. Now, what I did is I went ahead and said, well, this 1/2 times the 2/3, that's going to be 1/3, or just a 3 in the denominator. And then I knew that this is going to be the square root of u, which means it's the square root of the group 12 plus x squared. And then we have that raised to the 3rd power plus your constant of integration. This is the way that I entered my answer into Achieve, and Achieve counted it wrong. Well, it's wrong. That's a gorgeous answer. And in fact, that's the preferred answer. Anytime the original question has roots, your answer really should have roots. However, the answer that Achieve is wanting here is the equivalent solution of 1/3 times the group 12 plus x squared just to the 3/2 power. So it's, you could just go back up to this and say, well, yeah, of course it's 1/3 u, which is this group right here, to the 3/2 power plus c. So it's wanting that second answer. So please notice here on number 10, it took me 2 attempts because my first attempt, which is correct, they sadly counted wrong with the square root of the group to the 3rd power over 3 plus c. Should be the correct answer, but nay. So you just have to be a little careful sometimes. I would always recommend just going ahead and sticking with fractional exponents if you're wanting to be more like what they want the answer to be. That's not truly the best format of a final answer, but given we want to get the questions correct on the first attempt, it might be best just to leave them in that format. For number 11, we have the integral of x over the square root of x minus 9 integrated with respect to x. Okay, so that root of x in the denominator, I know that's going to cause trouble. So that was the first thing I did, is I want to get rid of that square root of x. And it doesn't help to let u be the entire denominator. I just want to let u equal just the root of x. Well, if u is equal to the root of x, then you could square both sides and say, well, that's the same thing as saying x is equal to u squared. Now, du here, if u is the root of x, then du, you'd say power rule 1/2 comes down in front. Then you have x to the negative 1/2 power with respect to x. I want to substitute for dx in the problem, so I solved for dx. dx, if you solve for it, you would have to multiply by 2, and you would have to multiply by an x to the positive 1/2 power on each side. So you have dx is equal to 2x to the 1/2 du. Well, please notice x to the 1/2 is u, so I can say this is nothing more than 2u du. So now when I go back to my problem, I already know x is u squared. I substitute that in. X is u squared. Dx, that goes in the numerator as well, is equal to 2u du. My denominator is just going to become u minus 9. So this is similar to an earlier problem we had. This time I'll factor the 2 out in front. My numerator is going to be u to the third. My denominator, u minus 9. Again, the instant you get that the numerator is of greater than or equal power to the denominator, you should instantly go ahead and say long division is your best technique to simplify. U minus 9 divided into u cubed. U goes into u cubed, u squared times u is my u cubed. U squared times negative 9 minus 9u squared. I subtract out that group, I'll get a 9u squared. U times 9u gives me that. And then I would have 9u times negative 9, that's going to be minus 81u. But we have to subtract out that group, so that minus a negative 81u becomes a positive 81u. Then you have to say, well, u times 81 will give me the 81u. But then that 81 has to also multiply the negative 9. 9 times 81 is 729. This will be a minus 729. But again, we subtract that group out. The u terms cancel, but we'll have a positive 729 left over for our remainder that's still being divided by u minus 9. So now I go back to my problem. This was my integral. I can say, well, my integral is going to become 2, so I have the 2, times the group. Well, what's the first part of the group? The first part of the group is the integral of the part that divided out evenly. So you'll see the integral of u squared plus 9u plus 81 integrated with respect to u. Then you say plus, we would have the integral of 729 over u minus 9. I just went ahead and factored that 729 out in front and said plus 729 on the integral of 1 over u minus 9 du. Now I can look at the inside and say, well, that one's easy because the derivative of the denominator is in the numerator. Thus, the answer to that one is the natural log of the absolute value of the denominator. These are all power rule integrals. This one's a natural log, so we can integrate. We'll still have 2 times everything inside of this group, and I'll get u to the third over 3 plus 9u squared over 2 plus 81u. And then, of course, this one's going to be your 729 natural log of the absolute value of u minus 9 plus our glorious constant of integration. At that point, I had to remember u is equal to the square root of x, or otherwise x to the 1/2. So this first term, you're going to get 2/3. X to the 1/2 cubed gives me x to the 3 over 2. And instead of putting the fractional exponent, I know it doesn't like powers within radicals, so I just called that the 3 over 2 power. The next term, you're going to have plus 9, and then u squared is just going to be x. Your next term, 2 times 81 gave me 162. We already know u is just the square root of x. You could have also called it x to the 1/2. It doesn't have any issue with understanding just square roots. It's when you have powers inside roots that it tends to count them wrong. So I put the root on that one. My next term, you're going to have 2 times 729 is 1458. Natural log of u is the square root of x minus 9. Please remember absolute value there, plus c. And just to let you see, this is precisely how I entered it into Achieve, and Achieve liked that answer. If I go to the next one here, number 12, you'll see for it gives me the integral of x squared over the square root of x plus 20. Now, I already know that the degree of the numerator is greater than the denominator, so at some point in this problem, I'm going to have to divide the denominator into the numerator yet again. You can't do that with that square root of x plus 20, so that's just not even possible in the first step. So the first step to this problem is, well, clearly a substitution. I'm going to let u equal what's inside of that square root, the x plus 20. Thus, x is equal to u minus 20. And then I can say, well, then x squared would be u minus 20 squared, or u minus 20 times u minus 20. They give you u squared minus 40u plus 400. Now, clearly, if u is equal to 1x plus 20, then du is equal to 1 dx, or just du is dx. I go back into my problem now. The integral of x squared, here I've showed what x squared is equal to, so that trinomial in terms of u goes in the numerator. Dx is simply du. My denominator is the square root of u. Now here's where you absolutely must distribute that square root of u into each term in the numerator. Remember, that's the same thing as u to the 1/2. U to the second divided by u to the 1/2 is u to the 3/2. Then I would have minus 40u divided by u to the 1/2 becomes minus 40u to the 1/2 power. And then this last term is going to become 400u to the negative 1/2 power. Now that you have all fractional exponents, you can integrate with the power rule. The first one becomes u to the 5/2 times 2/5. The second one, you're going to have u to the 3/2 times 2/3. 2/3 times 40 gives me the 80/3 out in front. The last one, that u is going to go to the 1/2 power. Then you would divide by 1/2, or in other words, multiply by 2. That's why we say 400 times 2 is 800, u to the 1/2, plus your constant of integration. At that point, the only thing I did was, in the place of u, please substitute what it's equal to, the group x plus 20 everywhere. And that is precisely what they were wanting for that problem. For the next one here, number 13, we had the integral of, or I had the integral of sine squared 7x times the tangent of 7x integrated with respect to x. So this isn't any one that we instantly think of, trigonometric identities being super helpful, but it actually is. So here's what I did. I knew that sine squared 7x we know is equal to 1 minus the cosine squared of 7x. Now, tangent, we just know is sine over cosine. So I got my sine squared written as 1 minus cosine squared, tangent as sine over cosine. And then here's what I was thinking. I was thinking, let's get all of my cosine terms together, and then I can let u equal the cosine of 7x, and then du is going to be the negative of the sine. This is going to be good for a substitution. So that's what I did in my next step. I said, let's call that 1 minus cosine squared 7x. I'll divide by the cosine of 7x here, which leaves this sine of 7x all out by itself. Please keep in mind, this is equivalent to what I had. But now it's more obvious in this format that all you need to do is to let u equal the cosine of 7x, and then du is the derivative of cosine, which would be the negative of the sine of 7x times 7 with respect to x. So I get negative 7 sine 7x dx. I have all of that in there with the exception of the factor of negative 7. So I just showed in red here. I'll multiply by negative 7 on the inside, but I would have to divide by negative 7 on the outside. So my integral becomes negative 1/7 on the integral of 1 minus u squared over u, and then everything else is just du. Similar to the last problem now, I need to distribute that u into both terms in the numerator. In the first term, I'll just leave it as 1 over u, because that will integrate to be a natural log. The second term, minus u squared over u, just becomes minus u. So we'll integrate. The first term is the natural log, the absolute value of u. The second term is going to be u squared over 2, and we have plus our constant of integration. Negative 1/7 out in front is going to distribute to both terms to give me negative 1/7, natural log of the absolute value of u, which is cosine of 7x. And then we would have a negative times a negative for a plus 1/14 cosine squared of 7x plus your constant of integration. Pretty straightforward problem there, as long as your careful about your initial trigonometric identities and getting all the cosines together. And then once you do the substitution after that, it's pretty straightforward. Number 14 here. Now, definitely you should know what to do in 14. The only thing in it is a natural log. Natural log is a clear indicator of integration by parts. So I don't know how to integrate the natural log, but I sure do know how to take the derivative. The derivative of every single natural log in existence is the derivative of what's inside divided by what's inside. So the derivative of the natural log of x squared plus 256, x squared plus 256 goes in the denominator. The numerator is the derivative of that, which is just 2x with respect to x. Now, the rest of it, which is just the dx, or you could think of it as 1 dx, integrates to become x. Now I can say for my integration by parts formula, u times v minus the integral of v du, u times v, I'll get x natural log of x squared plus 256 minus the integral of v du. So I'll get my 2x squared over x squared plus 256. Yet again, just like several other problems in this assignment, the degree of the numerator and denominator, they're the same. You've got to use long division. I showed that over here. X squared plus 256 divides into 2x squared 2 times. It's going to leave me 2x squared, and I would have plus 512. Then you need to remember you're subtracting that out. So you're going to get a remainder of negative 512. Now I go back to my problem and I can say, all right, this integral answer is the original u times v. That part's already integrated. And then minus everything that I get from this. Well, the first part of what I got from that, it's the integral of 2 with respect to x. That part divided out evenly. So I have minus the integral of 2 dx. And then I would also be subtracting, but this part's a negative, so minus a negative makes it plus a positive, and I'll factor out that 512. Instead of leading the 512 over that denominator, I factored the 512 out, and then I'll have 1 over that denominator. I recognize that denominator, that's the same thing as x squared plus 16 squared, and then coincidentally, the table of integrals formula that helps with that for the inverse tangent is number 16. You can say 1 over u squared plus a squared is 1 over a inverse tangent of x over a, precisely what we're going to do here. So a in this case is 16, so you'll see from this step to this step, I'm dividing by 16. 512 divided by 16 gave me the 32. And then I have inverse tangent of x over a, x over 16, plus your constant of integration. And of course, the only other thing was the simplistic step of integrating 2 with respect to x to get the 2x. And then this part was already done. All right, for number 15 here. 15, similar to 13 in that we have a sine function, but it's actually a little bit more natural because we have a cosine term with it. Soon as I see the sine and the cosine, I'm thinking, what do I work with? I want to work with odd powers of sine, cosine, tangent, and cotangent. I have the odd power of the sine. That's what I work with. How do we work with it? We rewrite all of the powers other than 1 in terms of cosine. So I know 1 minus cosine squared is sine squared. Sine squared squared would take care of 4 powers of this sine. So 1 minus cosine squared of 7x quantity squared takes 4 powers of that sine, and then there's the 5th power. I now go into my next step and I can say, well, that 1 minus cosine squared of 7x quantity squared, that's going to start my integral. I'll have a cosine squared of 7x by it, and then the remaining power of the sine of x, I'll go ahead and put right here along with a dx. Now I'm thinking, I would like to let u equal not the second power of the cosine, but just the cosine of 7x. And then I can say, well, if I did that, the derivative would have to be, derivative of cosine is negative sine. So this is going to be negative 7 sine of 7x, since the derivative of the angle is 7. And I'm looking up here, again, I don't have the factor of negative 7, but it's easy. I can just multiply the inside by negative 7. If I divide the outside by negative 7, then all of these last 3 terms here become du. and I'll have 1 minus u squared times u squared du. That's what I did right here, and it's bu to full. Of course, don't forget your negative 1/7 out in front. That didn't cancel out. The negative 7 did because of the substitution. Now, what I did from this step to the next is 1 minus u squared quantity squared. That would give me 1 minus 2u squared plus u to the 4th. I took that, distributed u squared throughout all of those terms to get u squared minus 2u to the 4th plus u to the 6th. At that point, you can just say we're going to integrate with the power rule, u cubed over 3 minus 2u to the 5th over 5 plus u to the 7th over 7 plus that glorious constant of integration. After you distribute the negative 1/7 throughout all the terms, you'll get negative 1 over 21. And since u is the cosine, you'll get cosine cubed of 7x. And then you'll have plus 2 over 35 cosine to the 5th of 7x. And then your last term would be minus 1/49 cosine to the 7th of 7x. And I ran out of room for the constant of integration, so I just put it there below. And just to double check here, 15, you'll see that that's how I entered it in and achieved like that answer as well. Now, for the second to last problem here, number 16, it was a pretty cool problem. Once again, it gave me a trig function. This one was the cosine to the 7th of 5x. I'll go ahead and maximize this screen again here. When I'm thinking cosine to the 7th of 5x, well, it's an odd power of cosine. How am I supposed to attack the odd power of sine, cosine, tangent, or cotangent? Well, you rewrite it all but one power in terms of another trig function. In this case, I know 1 minus sine squared is cosine squared. Cosine cubed would give me 6 powers of this cosine. Then I'll have 1 left over for the 7th power. So I know I need to rewrite this integral as the integral of cosine to the 6th, written as 1 minus sine squared of 5x quantity cubed, times the remaining power of the cosine of 5x right here. Now, that sets it up for me to be able to do substitution. I'm going to let u equal the sine of 5x. Then the derivative would be cosine of 5x times 5, or 5 cosine 5x. Now, the 5 cosine 5x dx, I have the cosine 5x dx in there. I don't have the factor of 5, so as frequently before, I multiplied the inside by 5, divide by 5 on the outside. Now the last 3 terms are going to become du in the next step. This first group is going to become 1 minus u squared raised to the 3rd. Now, you could either multiply out 1 minus u squared times 1 minus u squared times 1 minus u squared and do the algebra, or what I did is I just thought of Pascal's triangle real quickly, and I said, well, I know it's going to be 1 times the first term to the 3rd power, that's the 1. Then it's going to be plus 3 times the first term squared times the second term to the first. That gave me, because the second term is negative, so that gave me minus 3 u to the 2nd. Then this is going to be the coefficient of the first term to the first and the second term squared. So I have plus 3 times 1 times negative u squared quantity squared, which gives me plus 3u to the 4th. And then your last term in Pascal's triangle is the coefficient of the b term in here to the 3rd power. So you say, well, that's just going to be 1 times negative u squared to the 3rd. Well, negative u squared to the 3rd is minus u to the 6th. So however you get out that polynomial, whether you like Pascal's triangle or you just prefer to multiply it out yourself, whichever way, please get to this answer. And then after you do the algebra, then you can do the calculus. Power rule is all we need. This is u to the 0 becomes u to the 1st. This becomes 3u cubed over 3, which is just going to be minus u cubed. Then we have plus 3u to the 5th over 5 minus u to the 7th over 7 plus your constant of integration. We know u is equal to the sine of 5x. So we'll get 1/5 the sine of 5x minus 1/5 sine cubed of 5x, and then it would be plus 3/25 sine to the 5th of 5x, and then minus 1/35 sine to the 7th of 5x, plus your constant of integration. The last problem here, I like it, one of my favorites in the section. As soon as you see the denominator is of lower power than the numerator, you gotta say long division. I did that, and the long division is pretty short here. X to the 4th minus 1 goes into x to the 5th, x times x to the 4th minus 1 gives me x to the 5th minus x. We have to subtract that out, though. The x to the 5ths cancel, but then minus a negative x gives me plus x left over. Well, I know x to the 4th won't divide into x, so that's going to be my remainder. So then I say, well, then my original integral problem simplifies to be the integral of x with respect to x plus the integral of what's left over still divided by the original denominator. Now, I knew it wouldn't benefit me to leave that original denominator x to the 4th minus 1. Well, it's a difference of 2 squares. It would factor to x squared plus 1 times x squared minus 1. But x squared minus 1 further factors to be x plus 1, x minus 1. Now I algebraically broke apart that partial fraction here, x over, or broke this compound fraction into its partial fractions, x over x squared plus 1 times x plus 1 times x minus 1. I said, well, over the irreducible quadratic, I need a linear numerator of ax plus b. Over the linear factor of x plus 1, I needed a constant numerator of c. And over the linear factor denominator of x minus 1, I needed a numerator of constant d. I multiplied by the least common denominator on both sides. On the left, that gave me an x. On the right, you're going to have ax plus b times the other two denominators. You'll have c times the other two denominators, x squared plus 1 and x minus 1. And you'll have d times the other two denominators of x squared plus 1 and x plus 1. Now, once we have that in there, you can then say, well, all right, you should be able to solve for c by letting x equal -1. That's what I do. If x is -1, then the left-hand side of your equation is -1. On the right, you can see that the a and b terms would cancel because they're going to be multiplied by a factor of 0. Same thing with d, it'd be multiplied by a factor of 0. However, c is going to be multiplied by a factor of 2 and -2. Well, -2 times 2 is -4. I get -4c is equal to -1. Thus, c is equal to a positive 1/4. All right, I do the same thing for d. I can say, well, if I can let x equal 1, I should be able to solve for d. I try that. I can see that the a and the b terms cancel, the c term cancels because they're both multiplied by factors of 0. I'll have d times 2 times 2. Well, 2 times 2, again, 4. I get 4d is 1, thus d is 1/4 as well. Now, once I have my answer for c and d, I can then go back and work for my answer for a, because I can see that in this problem, b could never equal a coefficient of an x cubed term. However, a is a coefficient of x cubed, and c would be a coefficient of x cubed, and d would be a coefficient of x cubed. Well, on the left-hand side, you don't have an x cubed term, which means the coefficient of x cubed is supposed to be 0. On the right-hand side, it would consist of a plus c plus d. Since I already know c and d are both 1/4, I get a plus 1/2 is equal to 0, which then leads me to know that a is the negative of 1/2. All right, now, the way I solve for the remaining variable b is I looked at the constant. I said, well, there is no constant on the left-hand side. Constant is supposed to be 0. On the right, I could see that a could never equal a constant, but b would be multiplied by 1 and -1. I know negative b would be a constant, would not have an x term attached to it. The c constant would be c times 1 times -1, so minus c. And then the d, you would have d times 1 times 1, it'd be plus d. So then I can say, well, but negative c plus d, that's going to be minus 1/4 plus 1/4. Those two are just going to cancel each other out and give me a 0. I'd get negative b plus 0 is 0, thus b is 0. All right. So now I go into my problem. I went ahead and integrated the first term. The integral of x is just power rule, x squared over 2, or 1/2 x squared. Then my next term, this whole thing was broken down into these 3 partial fraction integrals. The first one, you have the a is negative 1/2. You know there's no b term in there. That negative 1/2, I went ahead and brought to the outside, and then on the inside you would have 1x over the denominator of x squared plus 1 dx. Now let's talk about why I did this red here. I could see my numerator and denominator differed by 1 power. And so then I can say, anytime that's the case, it is a natural log. Well, every time it's a natural log, the derivative of the denominator has to be in the numerator. Derivative of that denominator is a 2x. I needed to force a factor of 2 in the numerator, so I did. I multiplied by 2 on the inside. I needed to remember to divide by 2 on the outside. So now that's going to become a minus 1/4, and then this is just going to be the natural log of the absolute value of x squared plus 1. I move on to the next 2 terms. They're more simple. The plus the integral of c over x plus 1. I didn't want to put the 1/4 in the numerator. I factored it out and just said dx over x plus 1. And then you would have similarly plus 1/4 over x minus 1. I factored out the 1/4, the integral of dx over x minus 1. These last 2, of course, are both natural logs because the derivative of the denominator is in the numerator. Derivative of the denominator is 1 in those cases. So these would be plus 1/4 the natural log of x plus 1 plus 1/4 the natural log of x minus 1. I can say, well, if I have 2 logs that's being added, why not just go ahead and say plus 1/4 the natural log of the product x plus 1 times x minus 1. Now, I knew that this would be minus 1/4 here, so I just went ahead and put that in the exact same logarithmic function, but that term goes to the denominator. Remember, that means minus 1/4 the natural log of the group x squared plus 1. I just thought it was neat to kind of condense it down to 1. And then, of course, I left the 1/2 x squared out in front and added the constant of integration. And when I tried, I was a little worried because I was thinking that Achieve would not approve of the condensed version and it would have me wanting to write it out as the 3 separate logs. But fortunately, it did like this answer here, which this is, if you were putting the best format of the answer, this is the format of the answer, I would want you to put on a written test. So that's the good format. Sometimes Achieve doesn't necessarily want the good format though. So I was a bit worried, but it worked out just fine. I hope you do enjoy the problems within this section. This is an awesome section. And I will say, if you feel confident with the problems in this section, it's a really good sign. It's a sign that you are getting the techniques of integration extremely well. If you've really struggled through this section, then you're going to want to go back and brush up on your integration techniques. These techniques will never go away in future classes. You may have easier versions of some of them and stuff, but you'll never be able to forget certainly integration by parts, substitution, trigonometry within integrals, trig substitution, and partial fractions. All of these are just absolute necessary techniques. So this is probably my favorite section of the semester just because it does take some highlights out of each of those sections. Please make sure you're comfortable with everything in this section before you move on. It kind of goes downhill from here in the next section with improper integration. It's a pretty easy section and not nearly as fun. But just let me know if you have any questions. I'll be glad to help.